In this lecture, we will look into an interesting quantum transport phenomenon, which is called weak localization, which happens in the diffusive quantum transport regime. So, during this course of this lecture, we will look into the phenomenon of coherent backscattering, weak localization, and weak anti-localization. All right. So, as I mentioned, this happens in the diffusive quantum transport regime, where the inelastic scattering length and the dimension of the system both are much larger than the Fermi wavelength and the elastic scattering length. And this phenomena happens in a two-dimensional system which exhibit diffusive quantum transport, and this is also used as a tool to characterize the inelastic scattering length or phase breaking length in two-dimensional systems. Now, let us consider that you have a system with a lot of scattering points for the electrons. There are many scattering centers. Okay. Now let's consider, for example, the propagation of the electron waves from the point 0 to the point 7. Okay. So we are looking at one particular instance where electron is starting at a point which is labeled 0, and after scattering, after many scattering, it reaches the point 7. So as you can see from the diagram, from this cartoon, there are many paths the electron can take from 0 to 7. For example, I have labeled 7 possible, out of many 7 possible paths. One goes from point 1 to 7, point 2 to 7, point 3 to 7, point 3, 6 to 7, okay, and so on. Okay, there are many 0, 5 and 7, okay, 6 and 7, and there are also paths where it actually can undergo multiple scattering between points. For example, here these are 017, 027, 0467, but you can also have 042, again 4, again 2, again 4, again 5, 6, 4, 7 in random. It's completely random manner. You actually can undergo a lot of scattering events and reach 0.7 eventually. And that is true for the electron shuttling between any 2 points. This is just an example where we have considered point 0 as a starting point and point 7 as an end point, okay, and as the end point. Now, these are quantum transport phenomena. So, the probability or the total probability of the electron starting from 0 and reaching 7 is actually sum of all these probabilities, which are given by these wave functions, psi 7. You are going to sum j, psi j, where psi j is the probability for these electrons to take the jth path. And j are enormous in number. So each of these j is given by some tj, that is the transmission probability through that path, or you can say that is the amplitude of that path, and exponential I phi j is the phase term, how much phase that the wave is going to accumulate once it reaches between start and end point through that particular path. Okay, this is the wave function, and the probability is basically the square of this wave function. So P7 is the probability from 0 to 7 is square of this wave function here, okay? So this term, and that is the square of this term here. You sum and then square, not square and sum, because this is a quantum system where you have to sum the amplitude, then you square it. So when you do that, you are going to get the square of each of the path. When I say square, you have to take the complex conjugate and basically multiply with that. So when you take the complex conjugate or the exponential term, e to the power I phi j and minus I phi j form, they will all sum becomes 1 and you will left with tj square. Then there are closed terms where you are actually summing two paths and taking the square of that, okay? And all those will look like this, okay? Now there are n number of paths, and the phase difference is going to vary very drastically between path to path. What that means is, when I sum this over this cos phi j minus phi k, all those sum will eventually go to 0. Because there are so many paths for this, okay? There are so many it's a fastly oscillating term, phi j minus phi k. So it's a rapidly varying term from path to path. So the sum of all these for j is not equal to k will go to 0. That means you will get the probability as this P7 as sigma j tj squared. Okay, that is the probability of reaching 7 from 0, summed over all the possible path. Okay, so with that picture, let us look at what is the probability of coherent backscattering. Backscattering means it is the return probability, okay? It's a return probability. What happens if the initial and final points are same? In actuality, it doesn't need to be exactly the same point. If those 2 points are actually separated by distance less than the elastic scattering length, we are okay. Okay, because then the wave function is, you can think of like it is spread over in that small distance. So we don't need, what I am trying to say is we don't need to consider that it is 0 to 0. You can have a small another point which is very nearby, that is also almost like return probability. Okay, but let us consider the exact point. Okay, so let's look at what is the probability for one of the path, say jth path. Okay, 0 to 0, that means starting from 0 and you are reaching 0. And there are two possibilities for every path. That is, one is the clockwise, one is anti-clockwise. Or one is you can think of one is forward, one is the reverse. There are two paths which connects the same set of points. That means the Pj, the probability is Tj squared, Tj plus square and Tj minus square. One represent the clockwise and one represent the anti-clockwise. Okay. Then the closed term, phi cos phi j minus phi I. Okay. So there are two possibilities, right? What that means, let me also introduce or say here that Tj plus and Tj minus, you can assume they are same because the scattering or transmission probability doesn't really change whether you are propagating in the clockwise direction or the anti-clockwise direction. This is just for symmetry argument. You can think that these two are actually same. Tj plus and Tj minus are same, and this is then, so you don't need to worry about the difference here. So you have two paths, T cos phi j and phi j. I should put a plus here and I should put a minus here. Phi j and plus and minus. Okay, that is missing. Okay, so this one is actually the phase change, whether you go clockwise or whether you go anti-clockwise, you are at the same point. And the total phase accumulated, whether in both directions, is actually same. What that means is this term phi j minus phi k is 0, for the overall this term it becomes 1. Okay. What that means is this term Pj 0 to 0, that is actually for Tj square. Now this is the return probability considering one path. Now if you consider all the probability, you have to sum it over and for sigma j Tj square. So now what you are seeing here is there is substantial probability for this to come back. Okay, that is 4 times Tj square. Okay, amplitude of propagation, but there is a 4 times probability for that electron to return to same point. What that means is the forward propagating and the reverse propagating, they undergo constructive interference. That's what happening when you have phi j minus, phi j plus and j minus are the same phase. Whichever goes this way and the coming back this way, they actually undergo constructive interference, and the electron undergoes something like a localization. It is localized in that path. And there are multiple paths. So you can say that the electrons are actually kind of localized in all the paths, the forward propagating and the reverse propagating paths. Those undergo constructive interference and they are localized. And this phenomena or this situation is called weak localization. And this is actually a quantum mechanical effect. So what is the effect here? The effect is the coherent backscattering leads to an increased probability for the electrons to come back. Okay, that is this one. There is a probability for to come back to the same point. Okay, there is substantial probability. And that is because the time reversed twin paths undergo constructive interference and form a standing wave, causing a reduction in the conductivity. So the electron otherwise supposed to go forward, this is going to play a little bit of spoil sport for the electron to get localized in the system. Okay, that is going to basically reduce the conductivity, and this is a quantum mechanical effect. So this is something like you can think as a quantum correction. It's a quantum correction to the classical conductivity or resistivity. That is what weak localization is. Okay. Now let us look at how are we going to see this effect, or what situation or what behavior the transport will exhibit when you have weak localization or when you have diffusive quantum transport in the system. Okay. So again, we are talking about two directions, clockwise and anti-clockwise. And you need to basically, they undergo constructive interference, somehow you have to break it, you want to break that. Then you will not have the constructive interference, then you will expect what is the difference between transport when you have and when you don't have this constructive interference between the time reversed path or the localization. Okay. So when you apply magnetic field, and that is the recipe we have, okay, how to detect it? You are going to apply magnetic field. Classically, you cannot think of such a situation because classically, if you apply magnetic field, the particle will get deflected in opposite direction when you have velocities reversed. That means forward propagation will have one direction. We just say it has one k vector, and reverse propagation has another k vector, but they get actually reflected in opposite direction, and you don't have those paths doesn't coincide at all. Okay. Now the quantum mechanics, we know that magnetic field B basically affects through the vector potential A. Okay. So magnetic field B is given by del cross A, where A is the vector potential. A is the vector potential. is a vector potential. So the momentum, when you have in presence of a magnetic field, is given by mv plus q into a, where this is the magnetic field part, and q is minus e for electron, so mv minus e into a. That is the momentum. That's the momentum. Okay. Now, so now the K in presence of the magnetic field will get modified by this vector potential term. So now let's consider the path from 1 to 2 and 2 to 1. The reason I have drawn 2 points here is, as long as these 2 points are less than the elastic scattering length, these 2 points you can say as far as or less than the lambda f, the Fermi wavelength, you can say those 2 points are actually spread within one wavelength, So those 2 points you cannot distinguish. The electrons cannot distinguish those 2 points because they are the same point, because they are separated only by lambda f, the wavelength of the de Broglie wavelength of the electron. Okay, and they cannot separately scatter between 1 and 2 because those 2 points are much closer than the elastic mean free path Li. That is why I drew 1 and 2 separately. But this discussion here is unaffected, will be unaffected even if you consider 1 and 2 the same point. Okay, this is a general picture. Now, the phase difference when you go from 1 to 2 is 1 to 2 k dot dl, k is a wave vector, and so you have k is mv by h bar, so m into vf. Okay, that is because that is the velocity, Fermi velocity, because all the transport happens at the Fermi level. So Fermi velocity and mv by h. Okay, that's what you have. Okay, now similarly you also have this vector potential term E by h. Okay, now this is the phase change because of the normal propagation, and this is the phase change because the vector potential, presence of vector potential A dot dl. Okay, now you can, this is like a closed loop. Okay, because 1 and 2 are so close, it's a closed loop. So this term here you can basically replace by something called del cross A. Okay, because integral 1 to 2 A dot dl is same as the area integral del cross A. Okay, they are same. So when you do that, what you have is, this is your phase change because of the propagation, the absence of the field, and this is because of the field. Okay, and what you can get is, you'll get 2 pi e v dot ds. Okay, A dot dl becomes del cross A dot ds, but del cross A is the magnetic field B, that becomes B dot ds. Okay, and you are going to get 2 pi E by h eventually. Okay, now that is for 1 to 2. So when the electron takes the path from 1 to 2 in one direction, you get this. The other direction, when 2 to 1, this is going to remain, this thing will remain unchanged because it will accumulate same phase, whether it traverses this direction or other direction. But the vector potential is, the path and the vector potential are now in opposite direction, okay, to the previous path. Okay, so A dot dl term will change the sign, okay, because the vector potential has a specific direction. Okay, so in one way they are in the same direction, they are parallel, and you reverse the path, they are anti-parallel. So that term will change the sign. Okay, what that means is this phase difference between the forward and reverse propagating one becomes 2 pi e by h phi minus 2 pi e by h. So that becomes 4 pi e by h. Okay, the two waves now grow out of phase with the magnetic field or the flux phi. Okay, so that is what we have. So the magnetic field makes the time reverse trajectories dissimilar or out of phase. Or initially when they are in phase, they had a constructive interference. Now, as you turn on the field slowly, you are going to build a phase difference between those two, between the forward and reverse propagating path, and the time reverse start undergoing destructive interference, and you will lose that localization. Okay, so that is the effect when you have the field turned on. So what we just saw is that there is a return probability which is given by this term, and in the presence of a magnetic field, this phase difference delta phi, that is phi j plus minus phi j minus, that is the phase difference between forward and reverse propagating trajectories, okay, that is given by this formula here, 4 pi e by h into phi. 2 pi e by h into phi in one direction, and other direction the sign gets reversed, so the difference is 4 pi e by h into phi. So, and the summary is the magnetic field will cause a relative phase shift between the time reverse path, which will reduce the weak localization by destroying the constructive interference between the two paths. Okay, and this phi is the flux enclosed in that loop, which is given by the field into the area. Okay, what that means is the phase shift for any given field is going to depend on the area. But now what is the upper limit for this area? Okay, is there an upper limit? So to have the coherence over an entire path between say 1 to 2, that path length should be substantial, or it should be comparable or lower than the phase breaking length L phi. Okay, L phi. L phi is the phase breaking length. Okay, so the maximum area the loop can enclose is basically, if you assume a rough circular path, so S L phi is pi into r square. R is L phi divided by 2 pi square, where L phi is the circumference, divided by 2 pi will give you the radius. So this is like pi r square. Okay, this is of the form pi r square, and this will give the largest phase shift for any given field. L phi is going to give you, that path is going to give you the largest phase shift. You cannot get anything more than that, because when the path is larger, then of course the phase is not preserved, so you don't expect any interference between the forward and reverse propagating path, because that path length which is taken over that as a circumference of that area is basically not a coherent transport. In that there is no phase phase coherence along that path. The phase is not preserved. Okay, what that means is trajectories with larger area will enclose in statistically larger trajectories larger length will enclose statistically larger area. Okay, so what that means is the magnetic field, the critical field, which I am going to define as a field which is going to induce a phase change delta phi, is pi by 2. Okay, for one path. Okay, and pi by 2 for other path. Then pi by 2 plus pi by 2, that will be pi. That is, then they become completely destructive or out of phase. Okay, for one path, the pi by 2, the critical field BC is defined as it is going to induce a phase shift of pi by 2 for an area which is defined by the circumference L phi or SL phi. The 2 pi E by H SL phi into BC. That is how the critical field is defined. Now, H by E is the phi 0, the quantum of magnetic flux. Okay, and the critical field BC is defined as phi 0 divided by L phi squared H by E L phi squared. Okay, that is how the critical field is defined. Okay, so what that means is if the L phi is larger, then critical field will be lower. What that means, if you have a large coherence length, then the electron trajectory can be phase preserved over a larger area. Then a small field is enough to induce a phase difference because the area or the travel length of the electron is larger. But if the phase is not preserved for really large trajectories, shorter trajectories, then you need a higher field to get the same flux, because what we are interested is the LS alpha into BC, the product of the area and the field. That is a flux. Okay, so to get the same flux, if the area is larger, you need only a lower field strength. But if the area, shorter area is lower, that is path length is shorter, what that means is you need a large field strength to induce the same phase change, because the SL phi, the S is small, so you need a larger BC. Okay. Now here is an example where how the resistance, that is how you observe it, okay? How the resistance changes as a function of magnetic field. The effect of weak localization is a quantum correction to resistance, or an increase in the resistance or a decrease in the conductivity. That means when you measure the resistance as a function of the magnetic field, what you are going to get is you are going to get a peak at 0, because there you have weak localization. Then when you vary the field on either direction, the paths which actually contributes to the localization will grow out of phase and the resistance will decrease. Okay, and that's what you are seeing. And of course, that weak localization effect is also a function of temperature, and that's what is shown here in this work, where you can see lowest temperature, because you have far less number of scattering especially contributed by phonon, which has a strong temperature dependent. Okay, so your path length is very large, lower temperature. The area is large. Then you need only a small field. So to see this peak, then the moment you need a small field to destroy this effect, the peak will come down drastically within this very small range of field that you can see here itself. But now, when you increase temperature, you can see this curve is going to get flatter and flatter and eventually very flat. Okay. That means at higher and higher temperature, you need larger and larger field to observe this because your alpha is lower. So from this measurement, you can directly understand two things. Number one, what is the transport regime? Is it the diffusive quantum transport regime or not? Number one. Number two, you can also estimate the phase coherence length L5. Okay. So this is a very interesting, neat effect and very simple measurement where you can understand what transport regime we are actually in. Okay. Now, there is a twin effect to this that is called weak anti-localization. So, now we have not considered the effect of spin when we discuss weak localization. Okay. Or we have not really considered there is a spin flip. The scattering events are actually not spin flip scattering. The spin is preserved over both trajectory, they are same. But now there are special class of materials which possess high spin orbit coupling, where the spin and the momentum are actually locked. That means if the electron is going in one way, the spin is in one direction. The path is flipped, the spin flips and goes other direction. Okay, so one way you have one spin, other way you have other spin. That means spins are always anti-parallel. Okay, in that case, though your conditions of coherence between the reverse and forward propagating path are satisfied, but because of the spin states are opposite, they always interfere destructively. Okay, that means the two paths along one loop, the time reverse path will always interfere destructively. The spin is a magnetic field effect. Okay, it's kind of intrinsically magnetic, so it is not going to preserve the symmetry over time reversal. Okay, that means you will not have this weak localization, otherwise that should be present. So you will have an increased conductance because at that specific condition, when the two paths are destructively interfered, you have an enhanced conductivity or a decreased resistance. So that effect is just opposite of weak localization. The way that is going to figure out in the measurement is you will get an enhanced conductivity or reduced resistance in H0 B field. Then as you increase the field, rest of things will follow. Okay. So the correction of the conductivity is given by this formula, where B phi is the phase coherence characteristic field. That is the field where your phase coherence is field strength up to which the phase coherence is preserved. Okay, and psi is your digamma function. And this is this general equation where you need to substitute alpha basically equal to 1, -1 for weak localization plus 1/2 for anti-weak localization. That's what this condition is. And this follows from an experiment on a topological insulator, bismuth, antimony, telluride, selenide, okay, BSB, TeSe2. So here, you have, for this topological insulator, what you have is, you have spin momentum locked surface states, where the spin and the K or the momentum are actually locked. So if you propagate in one direction, you have one spin, the reverse propagation will have other spin. So it's already spin split the channels as shown by these two different colored paths. Okay, one corresponds to one spin, other corresponds to other spin. So they always interfere destructively, and there is no localization, or the localization which would have been there is lifted because of the spin degenerate is lifted. Okay, so this effect is called weak anti-localization, and this is a test to look at whether you have a spin orbit coupling in the system, or you can also estimate a spin orbit coupling energy from this one. Okay, and this also tests whether you have surface states such as spin orbit coupled. Okay, do have spin split state. Now all this, this is actually smoking gun for all this effect. Okay, so now what we have discussed in this lecture so far is the transport in two-dimensional system in the diffusive quantum transport regime, where we have coherent backscattering, which is going to increase the resistance, overall resistance, which is because of the interference of the forward and reverse propagating path, which will localize the wave function of electron, which should be otherwise propagating in nature. And you can lift this effect by the application of a magnetic field normal to the plane. And there is also an associated phenomena which is called weak anti-localization, which are twin phenomena, twin effect, where there is an enhancement in the conductivity or reduction in the resistance, which is caused by the spin dependent trajectory.